My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 449. In this lecture, we will try to understand model specific featurizations. Some featurizations work better for some types of models and other featurizations works better for other types of models. Let's take an example. We saw just a while ago in previous lecture that if you have feature F1, if you plot its PDF, let's assume you got power law distribution. Let's assume we want to apply logistic regression on top of it. We know that logistic regression is nothing but Gaussian naive-Bayes with Bernoulli's distribution on y-i's. What does Gaussian naive-Bayes internally assume? It internally assumes that your features are Gaussian distributed. Your real valued features are Gaussian distributed. That is the fundamental assumption that logistic regression or Gaussian naive-Bayes makes. And you have feature here. What is the feature? You have a feature here F1, which is following power law distribution, not Gaussian distribution. Your F1 is following power law distribution, not Gaussian distribution. In such a case, because we are using logistic regression, it makes sense to transform F1 into log of F1. To use this feature transform, this featurization is very, very problem specific. Because what did we say? Because we are using logistic regression, which performs better when you have Gaussian distributed features. Hence, we are making this transformation. This is one example. There is other example. Let me consider other example. This is example 2. Imagine if you have features F1, F2, F3 and you are trying to predict y. Let's assume it is a regression problem, which means your y belongs to real number system. Let's just say hypothetically we know that y is approximately equal to F1 minus F2 plus 2F3. Roughly, not exactly. And how do you know this? You know this, let's say, from domain knowledge, which means from domain knowledge you know that y can be achieved with linear combination of F1, F2 and F3. You can predict y roughly by having some linear combination. This is nothing but linear combination. Let me say we identified this linear combination with the help of domain knowledge. This is F1 minus F2 plus 2F3 is linear combination of Fi's features. In such a case, if you know this from domain knowledge, certainly linear models are better. Linear models like linear regression are much better, because when you apply linear regression, what do you get? You can easily get W1 equal to plus 1, W2 equal to minus 1, W3 equal to plus 2. If you set these values, this is what will you get? Y equal to F1 minus F2 plus 2F3. If you know from domain knowledge, again, this comes from domain knowledge and it is very, very problem specific. If you know from domain knowledge that y can be predicted using linear combination of Fi's, then it will make sense to use linear models. Again, this is very, very problem specific, and cases like this, y equal to F1 minus F2 plus 2F3, decision trees may not work very well, because decision trees do not have this linear way of combining things. Decision trees are basically if-else conditions, and decision trees cannot capture these type of relations. Y is approximately equal to f1 minus f2 plus 2f3 as neatly, as clearly as linear models. I will repeat, decision trees are basically if-else conditions, and decision trees cannot capture these type of relations y equal to f1 minus f2 plus 2f3 as neatly, as cleanly as linear models. Similarly, now let's take other example. Example 3. If you know that y is dependent on interaction of features f1 and f2. Let's assume again, we know that from domain knowledge, let's say this predicting gender, y is here predicting gender. You know that height and weight interact in very smart ways, because you know that people are they also tend to be hefty people, because you know that people are tall, they also tend to be hefty. But again, we also know that women behave differently from men, isn't it? When you know that there are these interaction between height and interaction which is height and weight, interaction between height and weight matters in predicting YIs, in predicting gender. It makes much more sense to use techniques like decision trees related methods like I can say random forest, gradient boost decision trees in practice in predicting gender when interaction matters, isn't it? Yes, it makes I will repeat, it makes much more sense to use techniques like decision trees related methods like random forest, gradient boosted decision trees in predicting gender when interactions matter. How do I know that the interaction matters? Because of domain knowledge. Because of domain knowledge or common sense, as you might call it sometimes. So which feature works from problems like this? Problems like this means gender, predicting gender, isn't it? From problems like this predicting gender, a linear model like logistic regression or linear SVM, linear model like logistic regression or linear SVM may not work very well, because interactions can be easily got in through using decision trees, as we have seen in previous lectures, like decision trees and decision trees, random forest, GBDT. All of them are tree based methods which are very good in capturing or accounting for interactions. Linear models like logistic regression are good at capturing linear combinations much more effectively. So sometimes what featurization works is also problem specific. It is also model specific. For example, bag of words. Let me take the example of bag of words, especially when you have text data. When you have text data, if you have text data, you do bag of words. Linear models tends to perform very well, because when you do bag of words, you end up having very high dimensional space, isn't it? A very high dimensional space. In a high dimensional space, as we have seen, when we learn linear models in very high dimensional space, you tend to have simple hyperplanes. In high dimensional spaces, you can easily separate your data into positive class labels and negative class labels. Since there are many hyperplanes to choose from in higher dimensional data, just finding a good hyperplane to separate positive labels from negative labels is not very hard, and for which classification or hyperplanes, the primary methods of separating positive labels and negative labels, it would be for things like linear SVM or logistic regression. Things like linear SVMs or logistic regression. The decision boundary for logistic regression and linear SVMs are hyperplanes. So when you have bag of words representation of text, which automatically creates a very high dimensional space, hyperplanes tends to work. Sometimes decision trees may not work very well. There are cases where random forest and decision tree work fairly well even for high dimensional space. I am not saying they just take a lot of time to train. Sometimes it is just a problem specific, based on what featureization you have used. The right model will also be dependent. The model you choose could also define what type of features would work better. That's what I want to clarify here. That's what I mean by model specific features. So if you have a model, let me say, if you have a model and if you have featureization, and both of them are interrelated. F means featureization, M means model. Some featureizations work better for some models, and some models work better with some form of featureizations. So they are related. So we have to be careful on using the right featureizations for right type of the models. Just go through this lecture. If you have any difficulty, please keep a comment. In my next lecture, that is in lecture number 450, we will try to understand one important concept, that is feature orthogonality. Thank you very much.